The ability to interpret a geological map is a fundamental skill for us scientists, and we can have a look at how to do this by using this small scale map from northern Britain. We're only going to look at a bit of it, the area of northern England through here, and our mission is to build up an understanding of the stratigraphic relationships between the main rock units and then to illustrate those on a cross section.
This is an old map published in 1948. I've made a copy of part of the map so you can follow along with this exercise by printing it off from the Shear Zone website. And perhaps before embarking on this exercise, you might want to refresh ideas about geological map interpretation by pre-watching this video that you'll find on this channel.
So let's take a look at the map. The geological units in here are shown by different colours, and these are identified in the key, but we're not going to use the key here. We're going to build up our understanding of the stratigraphic relationships from first principles. There are no topographic contours, so to get an idea of the relief, we're going to try and identify valleys from where the rivers are. But this isn't easy all the time because the map isn't totally clear. But we can have a bash in a few places. So let's scope around the map and build up the understanding first.
Okay, so we're ready to go. This is the map we're going to be using, and this is the direction of the cross section running west-southwest, east-northeast. But before we embark on the cross section, we're going to scope over the map, building up an understanding of the stratigraphic relationships. And before we do that, it's important to pick out faults which could obscure our understanding of otherwise simple stratigraphic geometries. So here are the main ones picked out in red, and this one through the middle and one down over on the bottom left-hand corner of the map are two that we'll have to consider when we put our cross-section together, and indeed as we build our interpretation. So we want to work out the stratigraphic order, and we also want to work out the dip direction of strata, and we can use a simple strike bar like this to show that. Now I find it useful, counterintuitively perhaps, to start with boundaries which have really complicated shapes, because this means they're much more likely to be interacting with topography, and we want the relationship between boundaries and topography to give us not only the stratigraphic order but also the dip direction of those boundaries. So let's zoom in on one part of the map here where the boundaries are indeed pretty complicated, aren't they? And let's pick out a river running through here. It's the River Wear, and we can see where the boundaries cross that river, they make pronounced V shapes here and here. So the boundary between the light blue and the green D4 unit and the D4 unit and the grey D5 are arrowed there, both of which V down the valley, so we have a dip direction this way towards the east-southeast, and we can take that information and plot it on the main map like this. Now let's confirm some of our understanding and get some more information on the stratigraphic order by moving to another complicated part of the map in here. So here's the zoom in, and let's look carefully and find the river valleys, and we can see in the bottom of the valleys that there are all these blue rocks, which are the D2 that I put with blue arrows, and on the hill tops we have the green rocks, the D4, so the blue units are underneath the green. There are outliers of the green D4 on the various hilltops over here, and this implies that the boundary between light blue and green is very gently dipping. It also means we've got to take some care, because these apparent V's in the outcrop shape of the boundary are because of the rocks going around the head walls of the various valleys. So let's take care and look at the river flowing directions, which are here and here, and we can see that in those cases there's a V in the downward flowing valley, which imply dip directions like this, which we can transpose onto the main map. So now let's assemble a rock succession. Those are the rock units, and we can see that the D2 unit is the deepest one, the light blue, and therefore presumably is the oldest, all the way up to the D5, the grey, which is the youngest of the three we've considered so far. And we can put the dip directions on generally down towards the east-southeast, towards the right-hand side of the map. But what about this unit here, the E prime? Well, from the topographic map, it's quite difficult to read where the valleys are, but we can find a few just in these corners in here, and these V's imply that the boundary at the base of the E prime dips down towards the east-southeast. But let's look at the relationship between the E prime and the D units that lie below. This boundary is not conformable. The E prime steps across as we go from north to south, from D5, D4 down to the light blue D2. So that's not a conformable boundary, it's an unconformity. Let's put this information onto our stratigraphic column here. So E prime sits unconformably above D5, D4, D2. But all the units continue to dip off to the east-southeast. What's underneath D2? Well, let's go to the central part of the map, which is west of where we've been so far, into this area here. We're not worried about that big tan area to start with. Let's look carefully, and we can see along the edge of the D2 is a spotter unit, very thin, that runs along like this. So that's what's underneath D2, a spotter unit in there. Something on the map that's marked with spots. And then what in turn is underneath that? Well, we can see just next door to the spotter unit in there, there's a tract of blobby lilac and purple rocks, which are quite difficult to interpret. But actually there's some more spotter units on this map here. And we can see that below this, we can see that it steps on units that are grey and purple and lilac colour. And clearly the spotter unit is discordant to those units that lie to its southwest. So we've got another unconformity. So the base of the spotter is an unconformity, and I'll just sketch it on like this on our stratigraphic column. The small scale map we're working with makes it difficult to tell the relationship from the map pattern alone between those older units, so we'll just plonk them in as a package. Right, so what's the dip direction for this second bit of unconformity? And again, it's generally hard to see, but in this position here, there's a V in the valley, so that the boundary, at least the spotter unit, dips down this way towards the northeast. Now what about the E and F unit that form those brown and tan colours through the central part of the zoomed map? Well, remember that their right hand or eastern side is a fault. It's this fault here that we identified right at the start of our map interpretation. So let's zoom back in and we can see the fault, but let's now start over on the older rocks and work towards the fault. So here's the unconformity around the rim of the older rocks that lie in that sort of wiggly semicircle shape, part rimmed by the spotter unit, but not entirely. So away from the older rocks and above the unconformity, we go into younger rocks. So there's a stratigraphic succession that youngs away from that unconformity. So therefore, the E and F, those orangey units and tan units, lie above the D units and are therefore younger than them. So we can put that onto our stratigraphic column. But notice that there's no E prime, no dark blue here. So we'll just fade that out for now and put the other units that we do have here that are younger than the D units in like this. There's an E and F and indeed a G package in here, all shown with those sort of orangey brown colours. And they lie above an unconformity with the D rocks. Notice that if we go and look a bit closer back at D in this particular area, there's an extra unit that we've not seen so far, which is shown by that sort of darker brown colour labelled D6 here. So we'll just put that into our key and our stratigraphic column as well. Now let's consider what lies above that higher unconformity and confront the problem of missing E. We can see that the brown E unit here is also missing as we walk around the outcrop trace towards the west. And we can explain all this by saying there's a pinch out onto the unconformity. Further to the east, presumably the E prime blue unit has already pinched out. So by the time we're in this map scene, we're in a situation where E is also pinching out, and then F1 to 5 is lying directly against the unconformity. And there is that unconformity. So an unconformity that lies at the base of the E's and F's, and another unconformity that lies at the base of the D. And we can put all this together onto our stratigraphic column. So that's our stratigraphic set of relationships. And we just want to make sure that we've got everything that we can put onto our cross section by looking carefully along the section line. If we look within the outcrop trace of the E sort of brown unit near the town of Appleby, we can see there's a little patch of green which is D4, which comes up from beneath the unconformity. So it's an inlier of D4, and it implies that the E units are very thin, and we can easily erode down into what lies underneath. And there's a similar outcrop pattern here in the central part of our map in an area that's otherwise all light blue. We'll come to what those pink rocks are, labelled 13, in a minute, but you'll notice that there's a little patch, a wing shape of B1, which lies beneath the D units. So there's another little tiny corner of the unconformity that lies at the base of the Ds. So again, the D units across the central part of the map must be rather thin. But what about 13? Well, we can see across the map there are little streaks and strips of things labelled with a numbered 13, shown with that claret colour. And some of them are quite easy to interpret. Here, they're thin and cut straight across the countryside, across valleys, and that they also cut straight across stratigraphic boundaries. So these are dikes. But in the central part of the map, the 13 unit is quite wiggly, and it follows quite closely and mimics the stratigraphic contacts. So these patches of 13 are igneous, but they're more likely to be a sill. So we'll have to take that when we come to put our cross section together. The dikes won't appear on the cross section, they'll be vertical and subparallel to our section line. The sills certainly should appear on our cross section. So that's our next game, to sketch a cross section to show all these stratigraphic relationships. And our first task when it comes to drawing the cross section will be to draw a topographic profile. Now, on regional maps like this, you generally just ignore the topography and just show it as a flat land. But because the dips we've seen are so low in some places, it's important to get a little bit of an idea of what the topography is doing. And we can use the drainage pattern to help us. So let's look at the drainage pattern along the cross-section line. And I've just picked out the direction the rivers are flowing. And we can use this to define two drainage divides like this. Towards the right of the right-hand drainage divide, there's a long area where the drainage is all going off towards the sea on the right. And that is a long topographic slope. And remember, it's in the direction of dip. There's another area on the map where the drainage is in the direction of dip, and that's here. And that runs into the area where the tan rocks are. And we'll use that information when we come to draw our cross section.
So having gathered together the various stratigraphic relationships and got an idea of the dip directions from the analysis of the map, the time's come now to try and sketch a cross section, and our mission will be to show those relationships on the cross section. So we'll extrapolate below ground and above ground to show those relationships. Okay, let's have a go.
So here's our line of section running west-southwest, east-northeast. And I'll just mark in the fault that's in the middle here, just to keep track of where we are as we go across the profile. And I'm just going to assume that it's dipping down towards the west-southwest. It's very steep. So now let's use the topographic information we got by looking at the drainage patterns and put this on to draw our topographic profile, something like this. And I'm going to start on the right hand side where the geology was very simple, that regional dip down towards the east to the right of the fault. Remember, we had a very simple stratigraphic order of D2, D4, D5, and the dips are gently down to the east-southeast, like this. We also inferred that the basal unconformity was quite close to the surface because of that inlier that we looked at when we were looking at the map. Now let's look at the geology just to the left of that fault in here, and we can see that at outcrop we've got those tan and brown units, the E and F, which I've just drawn in like this. Let's just zoom in. There we go. So we've got the fault dipping down steeply to the left. Above the fault to its left hand side we've got the brown, which is E, and the orange on here, which is the F1 to 5. Then to the left of that we've got more of the light blue, and there was that little patch of green that we saw as an inlier as well. So that's capturing the geology that we sort of interpreted from the map, and we can now project some of that light blue down underneath the E and F units like this. We can also see, if we move over to the western fault, that its left hand side has the orangey units that are E and F, something like that here as well. And when you put faults on a map like this, it's useful to show the down-thrown side with half arrows, something like this, to show the sense of movement. And we can do the same over here. Now here's why it's important to show what's been eroded, what's up in the air in our cross sections. I'm going to project the continuity of those brown units across the top of the map here to link the two faults, and if we do that we can see that the fault on the left there on the western side has down-thrown to the west. And now let's show the continuity of the rocks below ground. So I've drawn in the light blue against the fault, and I've shown how the other units connect up to that unconformity at the base of the E and F units, the beige that are in the sky. But that's not the only unconformity. What about over here where we had E prime here, and particularly show its relationship to the underlying units? And this means projecting E primed up in the sky across this region like this. And we can now show the truncation of the D units onto the unconformity as we saw in the map pattern further south like this. And it's always useful to add a lot of annotation just to explain our interpretation of these relationships. Finally, I've just shaded in with that diagonal grey ruling at depth the underlying rocks that lie below D. And as we said earlier, we don't really have enough information from the small-scale geological map to understand their structure. So I've just grouped them together and shaded them in like this. And I've added annotation now to explain some of the other relationships that we see. But that's not everything. What about the igneous rocks? Well, as we've seen, the dikes won't appear on the cross-section because they're running more or less parallel to the cross-section line, but the sills certainly will. So let's draw them on just above the base of the D unit like this. So we see it in the window, in the inlier, and we also see it against the fault in the middle there. So there's our cross-section with annotations. The next thing we could do is add a key to explain our stratigraphic units in the correct order. So there we have our quick cross-section and analysis of the stratigraphic relationships as shown on this small-scale map of northern England.